So we are dealing with problem number 2.2. So the problem is stating two identical vessels are connected by a tube with a valve letting the gas pass from one vessel into the other. If the pressure difference delta P is greater than equal to 1.10 atmosphere, initially there was a vacuum in one vessel while the other contained ideal gas at a temperature of 27 degrees Celsius and 1 atmosphere pressure. Then both vessels were heated to a temperature of 107 degrees Celsius. Up to what value will the pressure in the first vessel, which had vacuum initially, increase? So let us begin by understanding the complete situation in the diagrammatic way. So diagrammatically, this is the situation which we have. This is the initial condition which the problem has mentioned, and this is the final condition which the two systems will reach. So we have two vessels which are identical, having volume V1 equal to V and V2 equal to V. The temperature is 27 degrees Celsius initially, which is equal to 300 Kelvin, and at 1 atmosphere pressure. Now post this, both the vessels are heated to attain a final temperature of 380 Kelvin, and 380 Kelvin temperature is reached, and both the volumes are same. So initially it is containing N1 moles. So finally we are having N1 mole in this container, left container, and N2 mole in the right container post the valve opens. Now according to the problem, there must be a pressure difference of 1.10 atmosphere or greater than 1.10 atmosphere for the gas to pass from one vessel to the another. So over here we can say that delta P, which we are mentioning over here, is 1.10 atmosphere. So I hope the situation is understandable right now. So initially this was vacuum, that is at a low pressure condition, and this one is containing gas at 1 atmosphere at a temperature of 27 degrees Celsius or 300 Kelvin. Now as both the chambers are heated up, the pressure inside this chamber, which is the right chamber in the diagram, will definitely increase, and as a result of which, as you open the valve vessel, the gas will start passing from the right hand side to the left hand side, filling the vessel on the left hand side, till we say that a pressure difference of 1.10 atmosphere is attained, after which no gas will be transferred from this chamber or the right chamber to the left chamber. And what is important to understand is the number of moles of the gases remains constant. So we begin writing the molar equation. So we say initial gas was present only in the in this one is a second container which we take. So we take initially the gas present in second container. So in second container or chamber or vessel, so we take this one as Ni, and we say that the initial number of moles is equal to P1V by RT1. So initially P1 being equal to 1 atmosphere and the temperature being 300 Kelvin and the volume is V. And now finally the gas is present in both containers or chamber, and hence we say that the sum N final, which is equal to N1 plus N2. So if we write N1, we write it as PV by RT2, this time the temperature being equal to 107 degrees Celsius or 380 Kelvin, and in the other chamber the pressure is P plus delta P V by RT2. Temperature in this chamber is also equal to 380 Kelvin. And what is important for us to understand is that the number of moles initially and finally remains the same as the gas is transferred from one vessel to another or remained in the first vessel itself. So since N initial must be equal to N final, so we write the equation as that P1, which is equal to 1 atmosphere, so PV by RT1 or we are writing P1V by RT1 equal to PV by RT2 plus P plus delta P, that is the pressure difference value which is given to us, V by RT2. So V and R being common on both the side, we can chop them out and we get P1 by T1 equals P by T2 plus P by T2 plus delta P by T2. So over here we need to determine the value of P. Initial pressure P1 is known, delta P is known to us. So we over here to determine P, we can say P1 by T1 minus of delta P by T2, and then we multiply T2 on this side. So we can say P by T2, P by T2, 2P by T2. So 2P by T2, and this is equal to P1 by T1 minus of delta P by T2, and hence from here we obtain that pressure P is equal to half of P1 T2 by T1 minus of delta P. So this is the answer to the problem that we have. Now if we substitute the values which we have, so on substituting the values that we already have, so we obtain P is equal to half of 1 atmosphere multiplied by 380 Kelvin divided by, over here we have 300 Kelvin, and minus 1.10 atmosphere that is given to us. So over here on solving we obtain P is equal to 0.08 atmosphere, which we write as 0.10 atmosphere roughly. So this is the correct answer for this particular problem, problem number 2.2 in this series.